So my question is, with deep neural nets trained with backpropagation and rectified linear units, you already have zeros, zero activation for negative, some kind of gating units. So it looks a bit like selecting which part of the signal flows to the next levels. So do you think, is it equivalent or not? And why would it be more efficient to explicitly use a policy?
So it's not equivalent because here it's a probabilistic model. But I can say that here you have a probabilistic choice. So you have a probabilistic model. So it's clearly not equivalent. But it's very close to gating network, to what they call local computation, to what all the researchers call mixture of experts. So it's very close. The difference is the way it is learned, actually. But the idea of selecting, of choosing, okay, here you have an explicit choice, which is not the case with gating network. You are choosing first set of features, second set of features, so you have something which is discrete. And discretization is also, okay, in deep learning we are always making continuous function and continuous function and continuous function, but sometimes having something discrete is a hard choice, and it's very useful because it's very simple and you split your space and you say like decision tree. Here it's like that, here it's like that. So the idea, the basic idea, which is to specialize some particular computation to particular inputs, is common to gating network, local computation, mixture of experts, but the way it is done is a little bit different. And typically, with gating network, with rectified linear unit, you don't have this real ability of choosing between different network architectures, for example. If you are putting some translation of pictures, translate to right, left, down, you cannot learn this kind of thing. So I think this is more expressive because it's discrete. So you have a kind of combinatorial exploration also with this system.
And is it equivalent to say that you split the feature maps? You partition the feature maps and then you should pass? Because
you partition your space, your representation space at each level, yes. And depending on the subspace, you choose particular computations, but the system learns this partition. And here, this subspace is not the same as this one. So it's more complex than just putting features and split. But it's very close to decision tree. In decision tree, you do the same, but instead of having here a transformation of your input, you have here the input without transformation. But here you have this transformation. So,
how do you redefine the structure?
Like in a neural network, you choose an arbitrary number of actions, the size of your layers, you push button, you have a big cluster, you run 100,000 experiments and you choose the best. Yeah. And then you publish a paper saying, yes, I'm better than the other.
And then you apply to the real world and you observe that it doesn't work, right?
Yeah.
Thanks for the very nice talk. Looking at this graph, at, for example, the output, the last output layer, at N8, you actually compute the loss.
Yeah.
So in that case, maybe is it possible to actually look at this as a sequential game in which what you have at N8 would be like some sort of payoff, and you are trying to also, for example, you P and J would be like some sort of strategy. And then you could use game theoretic ideas to actually solve for the propagation probabilities.
Yeah. So this is a sequential process where at each time step you choose actions and at the end you compute some kind of signal. Okay. The difference between, let's say, games or classical reinforcement learning is that first, at each level you don't have external observation. Where you are playing game, you choose an action, you act on the world, and you have some stochasticity, the world is changing. Okay, so here we don't have external information, so it's much more easier than classical reinforcement learning. And here what we have is a loss. And the advantage of a loss in comparison to a payoff, or what we call a reward, is that a loss is a lot of information. Between you can derive a loss. So in the learning algorithm, what you have is this derivate of the loss. And if you have just a payoff, you are not able to compute that. If you just have a payoff, when you play a game, you have a payoff. If you lose, you know that what you have done is not good. But not the way you have to change your neurons in order to do better. You just know that your path is not good, which is written here, but you don't know in which direction to move.
But if, yeah, of course you can't derive the payoff for the reasons you just cited, but if you actually identify that stuff with the sequential game, then you have something else you could actually, for example, you look at the payoffs as the entries of some abstract matrix, and so that would be, I don't know, a matrix or a biometrics game, and at the end of the day, you could use it to go for
it depends on the nature of the payoff you have. But in the case of classical supervised learning, the payoff you have, the loss, is a rich information. While in reinforcement learning, the reward is very poor information.
Right. Any more questions?
Okay.
Okay.
Thank you.
Thank you.